Hello friends, I welcome you all to this video. We are with the first chapter of Advanced Digital Signal Processing, where we have dedicated whatever the fundamentals we have been learning here with the title Digital Spectrum here. So up till now in this chapter, with a difference to know between the continuous time, discrete time and digital signals, we have moved forward with the knowledge of the convolution, deconvolution, correlation, the modulation, digital filtering, the Fourier tools we have been learning so far. So thereupon we have undergone the introduction to Fourier series, Fourier transform, the various MATLAB demonstration for the concepts we have learned so far have also been completed. So it's time to learn what exactly the potential tool DIT FFT mean. So let us begin with the topic. So here we start with our topic DIT FFT. So DIT FFT stands for fast Fourier transform. This is the efficient way to have the computation of DFT what we have already learned into one of our previous lecture. So DIT stands for decimation in time. So now in this regard, whatever the input sequence we provide, that is represented as x of n, is to be splitted into the even indexed x of twice m and x of twice m plus 1, each with n data points. In general, what we do for computation of DFT, we represent DFT as x of k computed as the summation for n is equal to 0 to capital N minus 1 for this input x of n in multiplication by twiddle factor. The twiddle factor is represented W. In the suffix we have capital N, n point DFT, and to its power we have small k into n. And here this particular multiplication and further the summation is carried out for the range of k from 0, 1, 2 up to capital N minus 1 here. Now understanding this particular formula for DFT, we have this particular splitting. So by this particular splitting, we can represent the new formula for DFT, that is given as capital X of k, and capital X of k is into two terms here. So in both of these terms we have the multiplication inside, and this multiplication is having the summation operation outside. So this is the first summation for the index term m is equal to 0 to capital N by 2 minus 1 over x of twice m, what we have talked about. So this is x of twice m in multiplication to the twiddle factor W suffix capital N for 2mk, and this DFT is added to another DFT where we have the index term small m ranging from 0 to capital N by 2 minus 1 for x of twice m plus 1. This is the another part here. This is in multiplication to the twiddle factor W suffix capital N, and here it is small k here, and W suffix capital N twice m k here. So let us say this is equation number 1. Now this equation number 1 for the decimation in time fast Fourier transform is applicable for the values of k 0, 1, 2 up to capital N minus 1 here. Now next to that, if we are going to make the use of relation for the twiddle factor W suffix capital N to the power 2 here, if it is mentioned that it is nothing but W suffix capital N by 2, so that time to the above equation number 1 we can have the representation as capital X of k as it is on to the left hand side, summation m is equal to 0 to capital N by 2 minus 1 over the multiplication of x of twice m as it is into, here we have the change capital W suffix capital N by 2 to the power mk here. In the second term we have W suffix n by to the power k outside the summation operation. The summation ranges from n is equal to 0 to capital N by 2 minus 1 for the product of x of twice m plus 1 with W suffix n by 2 mk. So this is the change, and to this particular form of equation, let us name it equation number 2, and this is applicable for, again, k is equal to 0, 1, 2 up to capital N minus 1 here. Next to that, if we are going to define the new function as capital G of k, so this is equal to the summation m is equal to 0 to n by 2 minus 1 over x of twice m into this twiddle factor. So this is nothing but the DFT of x of twice m with capital N by 2 points. So we have splitted half of the points here. If it is 8-point DFT, here this will be the 4-point DFT. If the complete is the 16-point DFT, this will be the 8-point DFT that way. Now the another part is represented into the new part capital H of k here. So it holds the summation operation m is equal to 0 to n by 2 minus 1 for x of twice m plus 1 in multiplication to this twiddle factor where w suffix n by 2 to the power m k here. So this is nothing but the DFT operation over x of twice m plus 1 with n by 2 points. So for, let us say, total 16-point DFT, this will be the 8-point DFT, this will be the rather another 8-point DFT, or if it is the 8-point DFT, this will be 4-point DFT, 4-point DFT. This way we have to split it up. So the next equation numbers can be given as, let us say this is equation number 3 and this is equation number 4 it is. Now if we can note that capital G of k is nothing but capital G of k plus capital N by 2 for k is equal to 0, 1, and this time it will be capital N by 2 minus 1. So here it is in the bracket. Let us say this is equation number 5 it is. Along with, in the similar fashion, for h of k we can represent capital H of k plus N by 2 for k ranging from 0, 1, comma capital N by 2 minus 1. Let us say this is new equation, equation number 6 it is. Now if we can have the substitution of these two equations, just now we have done with the equation number 5 and equation number 6. If this equation number 5 and equation number 6 are substituted into equation number 2, so that time this equation will imply us the new equation. So capital X of k is equal to G of k. Added to, we have the twiddle w suffix capital N power k into capital H of k, and this is for k ranging from 0 to 1 up to capital N by 2 minus 1. So let us say this is nothing but equation number 7. Now considering the relation of capital W suffix N in the power capital N by 2 plus k to be minus of W suffix N to the power k. So that time, if it is equation number 8, the second half of the frequency we can obtain capital X of capital N by 2 plus k to be G of k minus W suffix N power k into H of k. This is the second term for k is equal to 0, 1, N by 2 minus 1 here. So let us say this is equation number 9 here. Now in this regard, if we perform the back iterations, the backward iteration, we will be introduced to the fast Fourier transform algorithm here. So there it will be the FFT algorithm. Now using the first iteration here, we obtain this particular diagram here. So whereupon we have the input sequence splitted into the two parts here, x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7 here. So the total 8 elements have been fed as input to the two parts of 4-point DFTs. So the complete example is of 8-point DFT, and we have the two splits into. So the first part will be giving us capital G of k here. So it ranges from 0, 1 to 3. In the similar fashion, for the second half, we have capital H of 0, 1, 2 and 3 here. So now to obtain the resultant capital X of 0, capital X of 1, X of 2, X of 3, X of 4, 5, 6 and 7, we have these particular relations here. So hereupon we have the representation of the twiddles, capital W, the suffix n, powers 0, 1, 2, 3 here, and here we have the multiplication of gain by minus 1 here. So this is the first iteration. By the second iteration, we go for the two types of the butterfly diagrams here. So here it is one part, this is the another part. So here we have the another splitting into the individual 4-point DFTs here. So now it has become 2-point DFT, 2-point DFT, and onto the latter part also we have the split into 2-point DFTs here. So here we have the inputs, small x of 0, x of 1, x of 2, x of 3, x of 4, here we have x of 5, x of 6 and x of 7 here. So in the same fashion we have the twiddles with the 0 power, with the 2 power, again 0 and 2 power, and at these places the minus 1 as the gains here. The twiddles are again here as in the previous diagram. So this is the representation of the second iteration to provide us the output sequence values. So these are capital X of 1, 2, 3, 4, 5, 6 and 7 here. Now by the third iteration we can go up to the 12 complex multiplication by this FFT algorithm. So here we have small x of 0, x of 2, x of 4, x of 6, x of 1, x of 3, x of 5, x of 7, and this way we have the 3 iterations here, and by the same kind of the twiddles at all these 3 places here, we come to the output value of the DFT. So that is capital X of 0, capital X of 1, 2, 3, 4, 5, 6 and 7 here. And if in the similar fashion, if we like to have the inverse or the reverse transformation, so that time we can call it to be the IFFT algorithm. So using the decimation in time, the 8-point IFFT algorithm in the iteration form can be represented as the change. You can notice whatever the IFFT is providing us, that it is the time domain signal here. Hence small x of 0, small x of 1, small x of 2, 3, 4, 5, 6 and 7 will be obtained as the output if we have provided capital X of 0 here, capital X of 1, capital X of 2, X of 3, X of 4, X of 5, X of 6 and X of 7 here. So by the 3 iterations we have this inverse fast Fourier transform made possible for the computation here. So by the next lecture, in the similar fashion, we shall be addressing the topic into the same chapter, and the topic will be DIT FFT. So it is the another approach, decimation in frequency, fast Fourier transformation. Thank you.